Okay, so welcome back to another lecture in this series of microprocessor systems design and interfacing course. In the last week we discussed about the instruction set. We just started about how to program using Keel microvision, and also we discussed about the very first set of instructions which are on the load and store, which are memory access instructions. So before we go into the rest of the instructions this week, and mostly we will finish off with the only instruction set and how to program some sample programs, for example, this week, and so that you will get hands-on on the Keel microvision to a good extent. Okay, so that's the idea. Before going there, actually just want to introduce to two set of documents which will be extremely useful, and you should download this and keep it with you for reference. So one is basically the technical reference manual from on Cortex M0 Plus, and the ID for this is basically this right at the bottom. You can see it over here. Okay, I'll put the documents in Moodle as well so that you can access it this week. So this is extremely useful for because you can see on the left hand side it has all the details of on from a device perspective on Cortex M0 Plus, and you go to programmers model, then there you will actually sort of has details on how to program Cortex M0 Plus. And if you go to instruction set summary, this is what we are discussing. So this actually sort of highlights all the possible instructions for Cortex M0 Plus, okay, and with the details. So if you want to go slightly more details, there's another document which is actually this, which is on the generic user guide, not the technical reference manual, because technical reference manual has some details on the hardware and the architecture as well, but this one is sort of purely, as you can see over here, there is a dedicated session, alphabetical order. You can find out details of all the instructions. So for example, we did discuss about LDR. So if I go here, so you have the LDR operations, so you can see over the details. If you click over here, all the details, everything is explained in very much detail. So in the class, in the lectures, I won't be going in this much detail because it's always there. It's more for me to guide you to some of these instructions, and rest is like you have to gain by experience, by using this, okay, by playing with this. So with that, let's actually move back to the lecture slides, and we did cover the load and store, but the next set of instruction is the data movement instruction. So as the name suggests, it is not with respect to data from memory or data to memory. It is more with respect to registers. Okay, so assuming that you loaded the data from the memory to the register, then how you can make use of these move instructions to move the data around within the register. So again, there are a bunch of options. As you can see, there is move S option and there is move option. So one thing I just want to highlight you, if the S option you are choosing, then it will actually be working only for registers R0 to R7. So if you let's say you put move S, okay, and some two registers which are beyond R0 to R7, it will give you an error when you build the code. Okay, so that's, you can also find out that error and then of course correct it, but it is good to know that whenever the S command is used, this is applicable to move, add, wherever. If you use that S, which actually gives the feeling that the flags are updated. So when you actually do the move S, it means that literally the flags will get affected. If it is symbol move, actually you don't have this, actually the flags may not get affected. But move command, you can use any register. There is no immediate or data byte, you can't really use move command. If you use that, again it will cause an error. It will only between registers. So that's the idea. So if you want to move some content of register to another register, you can use this. So RM is the source register and RD is the destination register. Okay, moves can be used for moving data. You can immediately give hash some data that will be stored in RD, but it is also possible to move between registers, but use only these registers. Anything beyond this, that means lower registers are supported, higher registers are not used. Okay, and there are options to actually move from special registers. We know that there are certain registers which are special registers, like program status register, control register, and all those things, which are beyond these 13 registers. So those register values can also be taken, or those registers can be written using this MRS and MSR command. So this is like move the content of special register to our normal register. MSR means move the content of our register, normal register, to the special register. So that's also possible. I have some examples coming, so it's fine. And there is something which is more interesting. You can actually use something like MVNS. Actually this is strictly not belonging to the data movement instruction, because there is a NOT operation also happening. So what it literally means is MVNS RD RM. What it means is like you will definitely move the content of RM to RD, but while moving that you will do a inversion of the values in RM. So basically move not RM. Okay, so not is like you are inverting the content, right? 1 becomes 0 and 0 becomes 1. So you just invert the content of register RM and then move to register RD. So it's a very interesting command. So you are in between, you are doing two set of things. Okay, so basically one is like you are moving definitely, but at the same time you are inverting as well. So it's like two operations in one cycle sort of. Okay, so some examples are here. So move R4 R5, it just means R5 will be moved to R4. So if you put, let's say, R10 here, it will create an error because that's not supported. Only sorry, it's fine. Okay, I'm talking about move S. Okay, if it is move S and if I put R10 here, it's not supported, because S will only support registers from R0 to R7. So here there is no problem actually, I'm sorry. So this just means that content of R5, copy the content of R5 to R4. R5 will keep the content, but R4 will be overwritten with the content of R5. MVNS R4 R5 means R5 will be moved to R4, not straightforward. You not the content of R5, basically invert the contents of R5 and move that to R4. That's what bitwise logical not of R5 will be moved to R4. That's a thing. You can also use the registers program counter and stack pointer, which also forms part of our register bank, right? So that can also be actually accessed using the move command. Okay, so that's the way. The meaning is very easy. Program counter content can be moved to R0 by using this command, and so on. And this is that special register option that I was talking about. So here the content of primask register, which is a special register, will be moved to, so it is that interrupt mask, those content register. If you go back and see the previous week slides, you'll understand what will be the distribution of primask. So that can be loaded. This is for checking. Let's say I want to, if I'm not using the debug option, but in the code itself I want to check the content of primask, I can do this option. Okay, so this move cannot be used to get access to special registers. If you want to get access to special register, you have to either use MRS command if to read from special register. If you want to write, you have to use MSR command. Okay, so you can play with, actually you have the Keel software hopefully installed in your system, so you should play with all these things and understand what is going to happen. So again, special register, if you forgot, I just copied the thing here. So you have the program status register, you have the interrupt mask register, which is the primask register, stack definition, which is the control register. So basically the important thing is like primask, for example, will give you the status of which interrupt is running on all those things. So if you want to intermediate, you check the status, you can use this command. Okay, so let me just quickly go to Keel and demo some of these move commands to you. Yeah, so next is arithmetic. So before moving there, let me just quickly show so that it's not terribly boring for you to watch this lecture. Okay, so I do have the move commands written to you. So this is pretty easy. So first of all, I'm loading the register R0 with some value. You can use the move also for the same, but I thought we will recollect some of those used expressions as well. So then you moving the content of R0 to R1. So move, you can use any register, there's no problem. Then move S, just to show you again same thing I'm going to do. Then MVNS is like literally you are inverting the content of R1 and then moving to R2, and then program counter content, you will see that getting moved to R. So some random, you can also play with this. I'm just showing you some random things. So let me build it first. There's no error, so you can move ahead using the debug option, and then you can just step these things. Hopefully everyone remembers now. It goes to reset handler. First is interrupt is mask, then it initializes. So all these initialization will do, and then it goes to main. Okay, and then you are going to, yeah, let's see, this R0 is some random number which was used during the system initialization, so that's why you see some random number here. But let's actually now loaded that R0 with this content. Now let's see, moving R1. So R1 is currently 0, so if I do this, it will smooth, and then of course move, this one is also done. Now let's see this. So R2 will not have R1 is nothing but this content, but it is inverted content. So basically 0 becomes F, all F becomes 0. That's the meaning of it. So you can see over here, so R2 is basically inversion of R1. That's what exactly happened. And similarly, the program counter, you can actually see what is a program counter, the value. This is the instruction which is getting executed. So if you see that, you can actually see the value which will come to R0. So this is currently 11C. So if I execute it, you can see the next value, right? Program counter will store sort of next value which will come to R0. That's what 11C. You will have the next one which is 120. Okay, so that's the idea. So hopefully you understood all the concepts now around the move concept. So I encourage you to highly encourage you to actually play with whatever is possible by combining the different instructions and so on. Okay, so moving on, let's go back to the slides. Okay, so hopefully, yeah, we discussed about all these concepts, and some of these examples I already showed you. Now let's move to the arithmetic instructions. So I won't be giving you examples for all the instructions and read out all these instructions, because that is terribly boring. It is there in that reference manual, and it's very easy to follow. You just please don't by heart, please don't by heart all these. Just refer to the manual all the time. Even if let's say in the ensum I ask you to program, I will give you the list of instructions. In fact, it's an open book, so you can actually refer to the instruction manual. Okay, so please don't by heart. There's nothing that you'll gain by hearting this. More than that is how to use this, how to cleverly identify a command which is useful for you. That's a key fact. Okay, so many things like add with carry, then add without any sign change. That means the flags will not be updated. Add as means the flags will be updated. The flags which are updated will be the negative flag, the zero flag, the carry flag, the negative or carry overflow flag, and so on. Okay, then there is an option to actually add a register with the relative address sort of. So you can play with all this. What's going to happen, you can actually literally see in Keel if you play with all this. And multiplication. Okay, so very interesting command. Then you have a reverse subtract, which is very interesting. I have an example in this. So one application for reverse subtract. Okay, so we'll during that time I'll explain. So you can subtract with carry, then subtract, all these very interesting options. So again, go back to the reference manual that I upload and see the complete details. But some examples are there in the next slide. So let's say, okay, so you're going to load register R0 with this content, and register R1 with this content. And if I add these two without any S command, so what is going to happen is the flags will not be set. Okay, so flags will never get affected, but we know that if I add R0 and R1, there will be an addition which becomes 0 0, all of them will become, and then there is a 1 which is overflowing. So there is a 0 getting into the register, so register R0 is becoming 0, and there is a flag which is actually the carry so the carry also is coming generated, right? Because if I add these two, there is a carry generated, and the result R0 will be all 0. So ideally speaking, the 0 flag and the carry flag should be set, but unfortunately, since we didn't use that S command, that will not happen. Okay, so that's the idea. So you just only consider the add value, the flag will be discarded. So this is an example. So I'm just making sure that here I'm loading R0 with 0, and then I'm updating the program status register to everything to be 0, so that we can see what is happening. And then if I do all these whatever written over here, okay, so you will see that there's nothing that is going to happen. Okay, so that's the interesting aspect. So we have both add and adders here. So if you put adders, what is going to happen is the 0 and the carry flag will be set. So let me quickly show this example so that it becomes very clear to you. Okay, or rather I will show you all the add examples together, because I have another one which is slightly more interesting, and I have made one code for all the things. So this is something which is very interesting, and it very often happens in our computers, because we do have probably a 32-bit microprocessor, but we may want to do a 64-bit addition. So how to go about it? So basically, for example, this is the addition that I want to perform. So how to go about it? So very easy. Actually, you might in the class I would have paused and asked you what should have happened. So you can pause the video and just think about it and see how shall we go about this. So idea is very simple. So we only have the option of 32-bit storage or 32-bit instruction. So what we need to do is we need to split this data into 4 data for each one of 32 bits. So this till this thing will be one data. So basically till this point will be one data, and then this will be another data. Okay, so that forms the first data, and this will be the first part of the second data, and this will be the second part of the second data. So you store in these in different locations, and then it's pretty easy. So it's something like this. So R0 will have this part, R1 will have this part, and then R2 will have basically this part, and then R4 will R3 R0, R1, R2, R3. So R3 will have this part, 4 part, and then you first add the lower parts R0 and R2. That's what happening, R0 plus R2. The result will be stored in R4. Okay, so that's the least significant byte, and then add with carry, because we need to take the carry. If there is a carry already happening from this, that carry should come and get added with R3 plus R1. Okay, so R3 plus R1 plus carry, and the result will be stored in R1. Okay, so that's the idea here, and that's it. So it's pretty simple, and let me actually show you this. Maybe one more example. I think let me cover all the arithmetic operations before I will show you the demo. Okay, so this is something very interesting. So I told you reverse subtract, right? So RSBS R1 hash 0 literally means that I will subtract 0 minus R1 and store that result in R1. So that's the meaning. So literally what is the result will be, if you go back and see that manually, you just take any 8-bit example and do this, you will understand that that is nothing but the 2's complement. Okay, so for example, let me store R0 with 4, and if I do this, R1 is R0, so that means 0 minus R0 will be stored in R1. So R1 will literally have the 2's complement of R0. So you can check it. So you just expand this to a 32-bit, which will be like 4 at the end, and then if I take 2's complement is something like you invert everything and then you add 1, right? So that's 2's complement. So you literally get this. Okay, so this is a 2's complement of 0x4. Again, please check it. Okay, so don't believe what I'm saying, just try and then come back to me. Okay, so that's the 2's complement. Yeah, so that we are almost there at the shift instruction. So now let me go back and show you this demo. Okay, so this is the sort of all the commands I put it together. So let me first build it, and then while I run it, I'll explain what each one means, and you could also mimic this. Okay, so again the usual stuff. So now you should be getting used to it so much. So let's go to the main now. So here, first step I'm basically doing is I'm loading R0 with 0, and then using the MSR command to clear the program status register. So program status register may have something which is coming from the system initialization. So I want to ensure that I clear all this. So I'm going to do that. So loading R0 with 0, and then clearing off. So you can see toggle bit we don't have control. That is basically the instruction set, right? So that's thumb, sorry, not toggle bit. Thumb is what t equal to 1 or 0 means, right? So it's sort of in that mode. It's saying it's sort of thumb 2 mode, which executes. It's ready for both thumb and thumb 2 instructions. So 16-bit as well as 32-bit instructions. That's the meaning of it. So we can't override that, but the flags that we are interested in, the N, Z, Z, N, Z, C and V, these flags are what the arithmetic and logical flags. So we are interested in them. Okay, and then now what we are going to do is we are going to load R0 with F and then R1 with 1, the command that we saw in the slide also, and then we literally add them without updating the carry flag. So that's what going to do. So let's say, so both of them, you can see FFF is here, 1 is here, and then I'm going to add R0 plus R1, result will be stored in R0. So let's see that. So basically if I add these two, you will get all zeros here at the R0, and then carry will ideally be set to 1, but since we are using add, it will not update the flag. So let's see that. Okay, nothing is changed in the flag. You can see R0 got changed to all zeros because I add these two, there is a carry overflow with the result being 0, right? So that's a big thing which happens many places in computation. Okay, so if I don't consider the carry, literally it means that R0 becomes 0, but that's wrong, right? Because there is a carry overflow, so you should consider that it gone beyond the 32-bit representation. That's what happened. Now let's again redo this with adders, not add here. So again I am going to reload R0 with the F value, so that's coming. Now again I am going to add these two, but this time I am going to use S here so that the carry flag gets updated. So you can have a look at these two, Z and C, because the result will be 0 and the carry flag will be set because there is a carry overflow. So let's do that. Yeah, you can see that both of them became 1, the result is 0, that's why 0 flag is set, and C is 1 because there is a carry overflow. Okay, so I hope this part is clear. Now let's move on to the other one, which is 64-bit addition. So it's quite straightforward. So this is the addition that you want to perform. So I'm going to store it in 4 registers, and then finally I will add the least significant word, 32 bits, and the carry also I will consider that so that I use ADCS, that is add with carry, and update the sign flag as well, so that you will, if you don't use the adders here, instead of that I was using add, we would have been in big trouble, because I should consider the carry also when I add it to the most significant 32 bits, right? So that's why very important to play with. So let's run this. So loading all the registers, which is done, and now I add the R4 is equal to R2 plus R0. At the same time carry and all the flags are set, and then use that carry as well. So R3 plus R1 plus the carry, that's what going to happen. And if you calculate, the result is actually 7. Okay, so please do that calculation. You will find that the final answer is 7, which is actually stored in R1. Okay, so I hope that's also clear. Okay, so please do that calculation. Please add this 64-bit. The answer should be this particular value. This is again 32 bits with the last byte, which is 7. Okay, so it's equivalent to 0111. Okay, so please remember that. Okay, so last but not the least, the reverse subtraction case, the 2's complement case. So we are going to load R0 with this particular value, and if I do this, RSBS R1 is equal to 0 minus R1, I'll get 2's complement of R0 in R1. That's what exactly this. So you can see over here, it's just the 2's complement. Okay, I hope it's pretty clear. Right, I mean it's very easy to understand, because the 1's complement or the inversion of this is like FF all F, and then this will be like 0 0 0 1 1 0 is this one, right? So it will become 1 0 0 1, and then if I add 1 to it, it will become sort of 1 1 1 0. So it is equivalent to C. Okay, so it's quite straightforward. Please do it. There is nothing magic about it. So we understood all the things. So this is the fun part, right? I mean, you learn the instruction, at the same time you should be able to try it out on the keel, so that you understand it very thoroughly. So I hope it's pretty clear. Okay, so let's go back to the slide again. So this is where we stopped, and now let me conclude this video with the shift part, and then we will have the rest of the instructions in the next video. Okay, so the shift instructions, very interesting and very important set of instructions. So you have arithmetic shift right, logical shift right, logical shift left, and then rotate right. Okay, so what are all these? Don't worry, we have some illustration here. Okay, and then I will show you also with the example. Okay, so arithmetic shift right. Okay, so what it means actually is, let's say you have a 32-bit value, and I will shift by some 3 binary positions. So you have to put the value 3 here. So essentially it means that everything will get shifted by 3. Okay, so problem is the last significant 3 bits will then basically go out, but there is an interesting thing happening. The second bit, okay, because it is 3, 0 1 2 will be discarded, right? So the last bit which is going to be shifted right will go to the carry flag. 0 and 1 will go, this guys will go out, right? So basically let me put it this way. So this guy will go out, this guy will go out, this 2 will go and sit in the carry, then this 3 will go and sit in 0, 4 will go and sit in 1, 5 will go and sit in 2, right? So that's how it happens, because you are shifting right. But more interestingly, what is happening actually in an arithmetic shift is whatever is the most significant bit, that will get replicated and fill these voids, because you are shifting everything by right. So there will be a void created in front, right, on the extreme most significant bit. So that gets replicated. So that's why it's called arithmetic. Okay, so the sign, whatever the, you can call it sign bit to be safer side, right? So the sign bit or the most significant bit, that will get replicated throughout. So if it was 0, then it will be just 0 getting into all these positions. Okay, so that's the idea. So I hope it's pretty clear. Okay, so basically you shifted everything by 3, right? So effectively what is going to happen is these 3 bits you have to consider. So this guy will come and sit here, this guy will come and sit here, this guy will come and sit here, and then these 3 bits will be actually the replica of the sign bit or the most significant bit. But the logic shift right will not do that. This will be 0. So that's the difference. So there's only one difference between arithmetic shift right and logic shift right. The most significant bit will get replicated in the case of arithmetic shift right. This will be 0 irrespective of the most significant bit. It will be 0 in the case of logic shift right. Similarly, there is a logic shift left. There is no arithmetic shift left, but there is a logic shift left. So that essentially happens is exactly same. Instead of right shift, you are going to do left shift. And then the interesting part is same like this guy going to carry flag, this guy will go to carry flag. Rest everything is exact replica of the shift right, because now you are shifting left. That's the only thing. Okay, and then the last but not the least, there is an option of rotate right with sign. So that's also there. So that means you won't throw out these values like in the shift right, but you will get sort of this like circular shift right. The values will just get sort of, so basically what is going to happen is, this is again 3, I'm showing an example you can play with. Okay, so this guy will get into here because you are shifting by 3. So initially it comes here, then another ship will go here, another ship will go here, so 3 times it will come here. So it's quite straightforward. I thought there is no confusing thing here. I will show you with an example. Okay, and yeah, I think this also. Okay, so we'll just a minute, I'll just check whether the code has only the shift operation. Yeah, so no problem, we'll just show the demo now so that it's pretty easy for you. So this is the code for the shift left, ASRS, LSRS, RORS, everything is here. Okay, so you can play with this code, and let's again build it as usual. So you learn everything, right? I mean, I'm doing it many times so that you learn all these things pretty clearly. So let's go through all this initial part, and then we are almost here. So I loaded some values, some interesting number here. So this is basically 800. So that means the most significant bit is 1, because it is 1000. That is 8 means it is 1000, right? And similarly the last one is also 1000. So let's see what happens if I do arithmetic logic shift right by 3. Okay, so let's do that. So basically what happened is R1, you can see over here, R1 is actually looking like F00. That means because it is 8, right? So the most significant bit is 1. So the 3 bits gets replicated. So it becomes 1 1 1, and then the last bit is already 1 because of the 8 1 getting shifted there. So you just do it manually. Let me just show it to you so that it's clear. We use the color. So what we had is like 1 0 0 0, right? Then all of them are 0, so we don't care, and the last one is again 1 0 0 0. So this was the case where we had the case of 8, right? It was 8 and then all zeros followed by 8. So this is, if I expand in binary, it's something like this. Now if I do this operation, what is going to happen is everything will get shifted by 3, but at the same time, since it's arithmetic, this 1 will get replicated. So it will be 1 1 1, and then this guy 1 is coming here, that's 1. And then similarly here it will be all this is 0, this is 0, and this guy will become 0 as well. So because all the things are shifted, and this guy will come here, so that's 1. So that is why it is F, then all zeros here, and then finally 1, right? So this is the value we get. So let me actually quickly show you that here, if it is the case. Yeah, you can see it over here. So that's what we got. And now logical shift right. So basically I again use the R0, same R0. If I do logic shift, only difference will be this F will not come because it is logical shift right, it will be all 0. So it will be 1 1 0 0 all 1, right? So let me do that. Yeah, you can see it over here. So that's it. Now let's see the logical shift left, what is going to happen, and the answer you should be able to figure out. So you can see it over here. This guy will go because 8 will go into the left side, it just gets discarded, but the carry flag might be set to 1. Not really, because carry flag also is 0, because it is 1 0 0 which is getting out, and the last 0 will go to the carry, so the carry is also 0. It doesn't matter, right? So you can play with it, just play with it. Change this to, I will have a suggestion here, change this to something like 9. Okay, change this to 9, or rather not 9, because it should be 1 0 1, then only the carry flag will be set. So 1 0 1 0, something like that. So it will be 8 plus 2, which is 10. So that means A B, right? A B B. You can put B here and see the change for yourself. But at this point, the carry flag is 0, because the 8 is nothing but 1 0 0. So third bit is 0, so it is 0. Okay, I hope I am not confusing you. You can just play with it. Don't worry. Okay, so this is the case, and now the logic shift right. Also, it's very easy for you to understand, because we already did this. This is the same. I think I just replicated it, sorry for that. Okay, these two are same. Now coming back to the rotating part, so this is very interesting. So where is rotation used? Just pause the video and just think about it. Where is really the rotation generally useful? Okay, or even shift right or shift, all those things, where is exactly it's useful? Okay, shift right, I mean rotation and shift right are very, very similar, except that rotation will be circular. So we will use this in mostly in sort of division. Okay, so shift right operation, if you think, it's sort of dividing by 2, equivalent to dividing by 2, because you are shifting every value by 2 to the right, so it's the value will get reduced by 2. Okay, so that's I'll show you the example. So let me load the value. So R0 is loaded with 8. So if I do a shift right by 3, it basically means I'm going to shift it sort of let's do that. Yeah, so you can see the answer got reduced to 1. So it was earlier 8, it became 1. So what essentially happens is 8, one shift it will become 4, another shift it will become 2, another shift it will become 1. So it's like dividing by 2 raised to 3. So that's 1, right? So that's what you got here. So it's very, very interesting, the rotating or shifting right operation. So I just use this to illustrate all the things. So I hope you are also enjoying. You should replicate this in your Keel software, play with it, use other examples as per your wish. So it's all at comfort for you. So just play with it and understand the possibilities. Okay, so that's it. So with this, I thought I will stop, or yeah, maybe one more thing I will cover, and then we will stop. Okay, so because it's time. Okay, so bitwise logical operations, let's try this. Okay, so this is also very simple. This is like bitwise I can do AND, or bitwise I can do something like this. Okay, so this is slightly complicated. It's like bit clear. So if it is something like this, BIC R2 R0 R1, so what we are going to do is basically this particular operation. So R0 and not of R1. Okay, so very, very complicated command, but yeah, I just don't think that it's not useless. Sometimes when you start writing the code, you think that, oh, this operation is useful, because when we study the instructions, like just for the sake of studying instructions, it looks like something is just manipulated, but it's not like that. This may be useful in some cases. We already saw about this in the previous slide, and there is exclusive OR, there is logical OR. Please try this out, because there's nothing really fancy about here. It's all about understanding here. So I will stop with this particular slide. Okay, so that's it from this lecture. We will have the next lecture, which will sort of complete the remaining instructions, and then we will stop for the week. I don't want to load you a lot in this week. It is just to cover the instruction set, so that you are very comfortable and you can start using the Keel software, or to that extent, when you come to the lab, you can start using the board straight away. Okay, so that's the idea. Okay, so with that, I will stop this lecture. See you in the next lecture. Thank you.